Good morning, everybody, and welcome to this morning's EDRMedeso UK webinar on conjugate heat transfer in Ansys. And I'd like to thank you for setting aside some time to join us in this webinar today, and I hope you find it very useful. So, just by way of introduction to kick things off before we get into the content, a little bit about myself. My name is Silvester. I'm the lead fluids engineer at EDRMedeso UK. I've been involved in simulation technology for just over 22 years now. Started out as a final year project doing a structural analysis and decided to embark on a career in CFD instead. Cautiously optimistic I've made the right choice. In between times, I spent quite a long time working for Ansys UK, so direct between 2007 and 2019 in a variety of roles, working through technical services, so supporting customers, delivering training and so on. Went into consulting, so delivering end-to-end simulation projects for customers, and then found myself in business development, so more on the commercial side of deploying services to our customers. Since last year, though, I've joined EDRMedeso UK, a channel partner for Ansys, where I am lead application engineer for fluids. A little bit about the company, if you're not familiar with EDRMedeso. It was actually started back in the 80s as a channel partner for Ansys simulation software over in the Nordics, actually as Sweden and Norway, and these two companies merged to form EDRMedeso, and a few years ago, following some expansion and growth plans, opened up offices in the UK. I'm actually based out of the Sheffield office in the UK. So these numbers need a little bit of updating. We've got more employees, we're growing quite a bit, maybe 50 or 60 technical staff. It's a little bit of a strange metric when you do this, but that adds up to something like 1,300 years of technical experience. So there's a lot of old heads in the company from Ansys, and also a lot of new staff coming in as well. So the UK team itself, here we all are from last year. That's me hiding in the background there. We have over 100 years experience between our old heads, and we've got some new people joining us as well. It's our role to distribute simulation software, to introduce simulation software to companies that perhaps haven't used it before, and I guess most importantly to ensure that new users are comfortable and confident and have the skills necessary to make a success of it. That's really what we're about. Now, today's webinar, then, just to go to an agenda, it's going to be kind of a mix between some of the slides, which really just sort of support what I'm saying, and I'll do some demonstration in the application as well, some live demo work. I tend to find that that tends to work best. So we'll go through a quick introduction and background into CHT, conjugate heat transfer analysis. We'll look at what we call the standard approach using purely CFD, and then we'll look at some of the other things that you can do beyond that, going into other simulations. It always starts off with your CHT analysis in Ansys CFD. And by the way, when I say Ansys CFD, I'm actually referring to a number of products. There's 5 or 6 different CFD solvers. I'm going to be demonstrating our flagship general purpose solver, which is called Ansys Fluent. So I'm sure many of you are familiar with that. I'll follow with a couple of examples. First of all, I'm going to do just a very simple CHT analysis of a simple solid component with a view to using that CFD to understand thermal stress and deformation. And as I've put up here, it's sort of a 5-minute, maybe 10-minute demonstration, just to show you how simple it can be. And that's in no way to underestimate the complexity of these type of analyses in real world cases. But in many times in CFD, you know, the physics and the setup and things like that are actually quite straightforward. Where it becomes complex is where we have geometric complexity. But for our purposes today, it's just going to be a simple run through end to end to show you the basics. And then we'll move on to another example where we'll dig into some of the modeling decisions that I need to make, that you need to make when you're doing a CHT analysis. go into some detail on things like radiation, for example. How is that handled? In CHT, we spend a lot of time thinking about walls. Walls suddenly become very, very interesting, and there's lots of different considerations as to how we simulate thermal interaction, conduction, and so on through walls. We'll talk a little bit about shells, which is related to wall treatments, and then go on to heat transfer coefficients. Again, something that you might think, well, a heat transfer coefficient is a heat transfer coefficient, but there's a few different ways of viewing that. And we'll finish up with a quick overview of a real world application case, just to show you what ultimately is possible, starting from a simple CHT analysis. So we've allowed an hour for this webinar. Realistically, I tend to talk for something like 40 minutes or so. I think that's a good time to talk, and there will be hopefully some time for some questions. There is a chat function here, so if you do come up with a question as I'm going through, please make use of that. If I don't see it pop up while I'm talking, I'll review that at the end. So I'm aware that for some of you it's nearly lunchtime, and for others it probably is, so I'm not going to get between an engineer and his sandwiches. I will do my best to stick to this timetable. So we'll move on to general thermal management in industry. There's hundreds of cases, applications where you would find the need to do CHT analyses. Personally, I've spent a lot of time in recent years picking up automotive type cases, so things like thermal underhood, exhaust, catalyst systems, manifolds, and things like this. And in these cases, the reason that you do CHT is most often because you're trying to mitigate or avoid mechanical impacts of thermal, let's say, mismanagement if you've got something wrong. So if your temperatures aren't controlled, then you get fatigue, cracking, and this kind of thing. So oftentimes we do the CFD with the end game result of performing some sort of structural analysis. A lot of electronics applications as well, particularly in recent years. We see things like huge server rooms generating lots and lots of heat. You've got to do something with that heat. You've got to take it away, make sure that component temperatures don't go above a certain limit. So there's a lot of CFD, CHT potential in those applications. And beyond that, we've got cylinder head here with valves, graphics cards, mobile devices, and so on. Everything's generating heat. We either need to take that heat away, control fixed temperatures, or in some cases we need to keep things warm so they're operating effectively. Lots and lots of different applications for CHT in the industry. Now, the reason why we do that is pretty straightforward. We've got to be safe. The products have got to be reliable. So, for example, these pressure vessels here, if there's any cracks or things like that, they can cause explosions and all kinds of things that we don't want. And then, of course, efficiency. When you're extracting heat, you're basically throwing away energy. Yeah, so we need to make sure our products are safe, reliable, and efficient, and that's really the motivation behind CHT analysis. So at its most basic level then, conjugate heat transfer is conducted entirely within a CFD solver. And in our case, we're looking at Ansys Fluent. So that's the standard approach. You can do steady state transient analysis, and what that will do is solve for the fluid flow in the fluid region, and it will simply solve conduction through the solid region. And then you can model or mimic effects such as transfer to atmosphere and so on. So that will give you an accurate thermal breakdown of the performance of your system. But then, as I say, it often leads on to more advanced applications. So CHT over here on the left, you can then start to think about parsing that CFD data to other types of analysis systems. So for example, there's one-way transfers. You might want to take data such as a heat transfer coefficient to a mechanical thermal system, which can give you stress and deformation and so on. You could also calculate the volumetric temperature of the solid in CFD and pass that on to a mechanical system as well. So in this case, we've got a circuit board here, and well, we're interested in a couple of things here: maximum temperatures, but oftentimes that thermal stress cycling of a circuit board, for example, that might be something we're interested in. And you can go further. If you've got transient or cyclic thermal loads, then you can start to look at two-way data transfers. And in a lot of cases, thermal analyses, we don't have a lot of thermal deformation, so one-way transfers work quite well. But certainly if you've got a cyclic thermal load, then we start looking at two ways. So CHT in CFD is almost always leading you somewhere else to other types of analysis. So it's definitely not something that you should think of as entirely contained within CFD. So what I'll do to get straight into the application here, I've got a very, very straightforward component here, an elbow, and this is the solid CAD of it, so I haven't done any work on the CAD as such. There's a cold inlet, a hot inlet, and as a consequence of that, you're going to get thermal stress and deformation in this component. And we're interested in knowing, is that within a certain criteria? So that is a very, very simple workflow to go through. So I'm just going to go over to the application itself now and take us through that. So I'll pull up Fluent here. I've got the component here, and what I'm going to do, I'm going to go end to end. So if you can imagine, you've just pulled in your CAD to Fluent, you haven't done anything with it, somebody's just given you some solid CAD, and you're tasked with performing a CHT analysis, simple CHT analysis, and then passing that on to a structural solver to look at deformation and stresses. So inside Fluent, I'm going to start by applying the mesh on this, and I won't go into detail about the meshing. I'll just run through the process because that's kind of another webinar, but you have to do it anyway. So what I'm doing here is just creating the surface mesh on the component, and then it's going to extract the fluid region for me. And if you haven't used Fluent meshing before, this is a kind of nice way of doing your CFD. You just have to bring in the solid CAD, and it sorts out the fluid zone and the solid zones for you. So I'm going to go on to creating the fluid region in here, and that's just going to do some work on the solid CAD there, and it's going to extract a fluid region. So it's just going to step through this, and you notice it's capping off these boundaries here, and it's just doing the last one. And now I can create my fluid region. Okay, nice, that's exactly what I want. I've got a fluid region and a solid region for the solid heat transfer. You can't see the solid region there, but it is there, believe me. Update the regions, and now I'm going to generate the volume mesh. Now, of course, in reality, for those of you that have done CFD before, you do have to put some time into getting the mesh resolution right. That's a sort of iterative process. So you may run a CHT analysis and maybe run a refinement. That's kind of basic for any sort of analysis. And okay, so we've got a mesh here, typical CHT mesh. You see we've got the solid meshed, we've got our fluid zone, I've got some boundary layers in there. And with thermal CHT analysis, getting the right number of boundary layers or getting that refinement is much more important than it is anyway, because thermal boundary layers can be very, very thin and very sensitive. So you do have to just put a little bit more due diligence into making sure that your inflation boundary layers are good. But for this example, that's fine. We've got everything that we need. So I'm going to head over to the solver side of Fluent. And Fluent basically works in two modes. It does the pre-processing here, and then you change into the solution mode. And what it has to do, it has to shift data around in the background, which is what it's doing now. And there'll be a lot of messages flashing up and warnings and what have you. Fluent is very verbose, actually. It's always telling you what it's doing, which I guess, it's better than it saying nothing at all, but sometimes you get so many messages here. Okay, that's fine. So I'm just going to display the mesh now, just so we can see what we've got. Okay, that's a simple component here, and you can see it's already set up boundary types for me. So it's a simple case now of just assigning material properties to my CHT analysis and assigning boundary conditions. And with a simple case like this, where you're just running an incompressible flow, you're just looking at conduction, that's really all you need to do before you pass it on to another type of analysis, such as mechanical. So I'm just going to check the materials first of all. So under physics here, I've switched on the energy equation. Turbulence is already switched on for me. And inside materials, I'm just going to use the standard database that's available in Fluent. So I've got steel there, which is fine. And for the fluid, I've got water there. And I just need to assign those to the cell zones. So I'll check fluid is set to water. Yep. And the solid one, I want that to be set to steel. Okay, so now I can just set up the boundary conditions, and in Fluent you can do this pretty much graphically. So I can just select the boundary, and you see it pops up the most relevant conditions here. So I'm just gonna, I've put in a velocity magnitude, assuming it's incompressible. I know the flow rates, and I've put in a temperature. That's okay, and I'm going to do the same for this one here. Up it pops, 0.5, 450. That's okay. And I'm going to close that down. And for this simple case, that is enough to get a solution. So I'm going to initialize that right away. And we're just going to perform the calculation. Now that's a simple case like this should take a minute or so to converge. And it should converge in around 60 or 70 iterations. So we're just watching the monitors come down to a convergence criteria. And with CHT, you notice that energy is always much, much lower than the other equations, and that's generally the case. You do have to converge energy down to a much tighter tolerance, and you do have to check that it's converged. Sometimes your flow can be converged, but your energy equation isn't. So it's something that you need to be aware of in CHT. Okay, so that's a simple, very quick CHT analysis. I'm just going to let me create some graphics here so we can see. I'll create a scene. There's always an odd expression, so we can see what we've got. All right, so very simple. Got a contour through there. There's the hot liquid, and you can see that it's conducted through the solid region there. That's pretty much what we'd have expected. Now, to take that further, let's say we are interested in, let's say we're concerned about these temperatures, for example, and the impact that might have on the structure. It's very simple to do that using the workbench operating environment here. And for those of you that aren't familiar with this, these system cells or tables represent a different types of physics analysis. So I've got my CFD CHT analysis here, and this little connector here, I'm pushing volumetric temperature that it's calculated from the solid into the mechanical solver, okay, so that I can use that as a boundary condition for a structural simulation. So I've just told Mechanical now to pull this data across, and I'm going to go into the mechanical interface. And for those of you that are sort of strictly CFD, I guess I used to be strictly CFD at one time many years ago, but since then, the technology that pulls the solvers together has made it very, very easy for somebody from one physics to go and start doing something in another type of solver here. So in Mechanical, I've got the same geometry, which is shared, and I've set up quite a basic analysis. I've put in a fixed support for these flanges. There's lots of other conditions that you can put in Mechanical. You can do stuff with bolts and sliding supports and all kinds of things. For our purposes, it's a fair assumption that these are fixed. And I've got my imported load from the CHT analysis. So I can just bring that data in now. And that's going to apply a volumetric temperature, okay, to my geometry. You can see that looks sensible. That's great. Now I can perform my mechanical solve. And again, in Mechanical, you can plot all kinds of outputs. In this case, I'm interested in the deformation here due to that thermal stress, and you can also plot your stresses as well should you have some kind of criteria that you don't want to exceed. So that was a very quick, very simple demonstration of what you can do with a CHT analysis combined with Workbench and combined with Mechanical to analyze deformation and so on. Of course, though, there are more complex considerations that we have to take into account. So what I'll do is, if I go back to the slide deck now, okay, I'll run through a different case here. This is electronics cooling example, and I'll just dig into some of the decisions that I've been making and some of the things that you will need to think about when you do CHT analysis. So in this case, and by the way, if you're not interested in thermal electronics cooling, that doesn't matter because the physics are they're the same. It's conduction, it's convection, it's radiation, it's dealing with thin surfaces. You get that kind of thing in pretty much all CHT applications. It's always very difficult to find an example that means something to everybody, but this is from a physics point of view, this is fine. So in this example, we've got a chip which is emitting a known power, okay, which is converting itself to thermal energy. That gets conducted into a heat sink, another solid region here, which sets up a natural convection flow. Now, actually, this component is vertical. That's the orientation, but for the purposes of the presentation, it fits better on the slide horizontal. So just in case you were wondering. We've also got a solid circuit board here, and oftentimes we're interested in looking at thermal planar conduction through here. So we can look at stress analysis and this kind of thing. And we've got a thin outer casing. So another problem that some of you might be familiar with when you're dealing with thin walls and baffles and things, that presents a bit of a meshing problem, but we'll come to that in a little bit. We've also got thermal energy being removed by radiative effects from this. There's a lot of temperature here, so we've got to take into account radiation. And a general objective for this kind of thing might be that, well, we're interested in keeping the maximum temperature of our chip below a certain value. So let's go back to Fluent, and I've got the case loaded up here. Let me just display it so we can see what's going on. Okay, so here's our chip in this orientation in reality. And what I'll do, I'll just display the mesh on there so we can see in a little bit more detail. So I'm just going to switch on the edges. Okay, so you can see I've had to mesh the solid, and you get these very thin cells. And ideally, we say, well, if you're going to mesh a solid, then you want maybe 3 cells across there to get a nice gradient. That then presents some challenges, which we'll come to. Same with the component itself and the heat sink there. All of this is meshed. Now you'll notice that the outer wall here is a thin surface. So again, typical in these applications, you get to heat shields and things like this, and they're so thin that you can't realistically mesh them. So we need a slightly different approach for that. But I'll come to that in a few minutes. So first of all then, if I go to physics, we've got the energy equation switched on. In this case, I do need to take into consideration radiation. So I can switch on my radiation model here. And as with all things in Ansys Fluent, when you click on radiation or the viscous, which is turbulence or something like that, you're immediately presented with a number of options. And it would be great if it was just radiation on or radiation off. But the reality is that the same with turbulence. There are models which are specifically designed for certain circumstances, and that's why you have a selection, as in Ansys Fluent. So we've got Roslin P1, S2S, discrete ordinates, and Monte Carlo. Now together they cover most of the applications that you would need to deal with. Just to have a quick word on radiation modeling. A lot of times in CHT, certainly if you're dealing with non-participating media, so basically relatively clean air between hot components, we use this surface-to-surface approach. And what we're doing here is the CFD program basically calculates a ray trace between every facet of every surface to every other facet. So in that way, it can compute how much energy is transferred by following those ray traces. That's basically how it works. And it does work very well for things like automotive underhood, space technologies, obviously stuff where you're working in a vacuum. But that's not to say it's right all the time. And there are ways that you can pick a different radiation model, but this is basically what it's doing here. So I'm not going to worry too much about these equations here, but just for your purposes, as long as we understand it's calculating view factors, that's essentially how it works. So I'm just going to switch my laser pen back on. Okay. So other radiation models, if you're into radiation, it's a little bit of a strange phrase that. If you're familiar with radiation, let's say, you'll know about optical thickness, and this is basically how you judge which model to use. They are geared towards different optical thicknesses. So the S2S model here, which we use a lot of in CHT, is designed for 0 optical thickness or non-participating media. And then we have other models which can suit other circumstances. So you just have to look at your individual circumstances. Okay, so we'll go back to the model again. And we'll look at a few other considerations. First of all, there's materials. A big part of CHT is getting materials correct. So now in this case, let's look at the solid materials. That's what we're generally most interested in. Fluent does have a database of basic solid materials, and here they are, but you probably noticed those keen-eyed of you, we've got Granta MDS database there now, which has a very comprehensive selection of materials which have been added in. So based on that, it would be very easy for you to find a material. If it's not exactly the one that you're using, it would be very, very similar. So next time you go into the materials panel, do make sure that you check that out. There's a lot of ways that you can define material properties for materials. So for example, if you've got a variable conductivity here, you can very easily put in polynomials or linear relationships, expressions, and so on. So for example, if I wanted to specify 3 points on a curve, I can do that quite easily. And what's kind of nice about it is that it does plot that as you're working. Okay, today it's not plotting it for me, but it should be. So I apologize about that, but that's live demos. Other aspects of thermal conductivity though are things like anisotropic conductivity. Oftentimes you've got materials where you don't have the same conductivity in every direction, so it's important to be able to handle anisotropic conductivity. So between these options here, you should have everything that you need to characterize your material. Now, it would be nice if everything's just constant, but many times things aren't. So we'll leave that simple for now, and I'll head over to the cell zones and the boundary conditions. Now in cell zones, you can see I've got a fluid and I've got 3 solids here. Now in this case, because I've got a heat source in this solid, I can add that directly using a source term right here. And I can click in source terms, edit, and you can see I've actually specified an expression. Expressions came into Fluent a couple of years ago. They were ported over from CFX, and they're a very, very useful way of defining inputs or things like boundary conditions in relation to other solution variables. And you can see here, I've got a power rating divided by the volume of that heat source. So it's just giving me watts per meter cubed. Very simple expression, but it's very nice to be able to do that. You've got access to all of the variables, so you can have sources or material properties which are functions of calculated variables and so on. So it becomes quite a powerful functionality in Fluent there. So that's enough to define the solid zones. I guess the only other thing you need to do is specify a material, but it's very simple to do that. and then we go over to the boundaries, and this is where we need to spend perhaps a little bit of time. Things like inlets and outlets are pretty self-explanatory. You're just defining what's coming in, maybe a velocity inlet, maybe a pressure inlet. That's fine. Where we get the sort of complications are when we start looking at walls in CHT analyses. So if I just click on this outer boundary, and you can see it's brought up the basics here. I'll click on more to give me all of the details. So this is all of the information that you can put into a wall boundary. Now, if I click on the thermal tab, you can see that I've got a lot of different options for specifying thermal conditions on that boundary. So at its simplest level, we're just saying, well, there's zero heat flux, it's a perfect insulator. Might be a fine assumption, it depends on the case. We can specify fixed temperatures, maybe a convection coefficient if it's exposed to atmosphere, radiation boundary, and then of course if you want everything together, then you can have a mixed boundary. It really depends upon what you know about the situation. One thing that you may have noticed already, though, is that we've always got this problem with thin boundaries, and there's a couple of options here that I want to illustrate. I'm going to go back to the slide deck to do this. So this is the sort of problem that we have. This is a in principle thermal underhood. Now you can imagine there's lots of thin baffles and shields and all kinds of stuff which would be really nasty to mesh. So we have to come up with ways of dealing with that. As I say, it's simple in theory, but thin surfaces can give us a real headache. So there's a number of ways that we can do that within Ansys CFD. So there's three basic options here. Number one is the difficult option. We mesh the solid, and that's great because it's the most thorough option, gives us full 3D planar conductivity, but it can be very, very tricky, and it's all very well me kind of sitting here with a rectangle, but you know, real world cases, it can be really tricky, and it can lead to very high mesh counts and so on, and give us a bit of a headache. So then you can go in the opposite direction, the opposite extreme, and you can just forget about the solid and just specify a virtual wall thickness. Now let me put my pointer back on. That's it. So what we do here is we get rid of the three-dimensional solid, forget about that, which makes our life easy, but then we've still got to account for conduction through it. So what we can do is just specify a wall thickness and do one-dimensional Fourier conduction through there. Now, in some cases, that might be fine. If you're just extracting heat from a domain and that's all it needs to do, then that's okay. But in a lot of cases, you do have planar heat transfer to consider, and that becomes important. So what we need is a sort of a compromise between these two, and that's where option 3 comes in, which is shell conduction here. So these are virtual cells. Again, we're not meshing the solid. Fluent creates layers of virtual cells in the background, and that means it can go back to calculating 3D planar conduction without the overhead of having to mesh the entire 3D solid. So just to sort of illustrate that a little bit more, what we're doing, we're creating a number of layers that they don't exist physically as such, but they're just there in terms of the computation. And what's great about that is that you can quickly model thin coatings, multiple different coatings, in a very efficient way. And you can see you have numerous layers with numerous different properties. So there's an example of that. It's, if you can imagine, if you cut a car in half and you looked at the exhaust pipe down here and it's radiating a lot of heat, you might have a heat shield here, which is very thin. And if you use shells, yeah, the result is exactly the same as if you'd meshed it with 3 layers. And that's actually just using 1 layer. So it's much, much more efficient. You can see the problem that if you don't take into account planar conduction, so the black line there is quite erroneous. The temperatures are too high because it's not spreading out. Okay, and actually just to point on this graph, the red line is exactly behind the green line. So that's what we're trying to get across here. The results are exactly the same. So just another example there, an underhood part validation. We've got the solid meshed with prism cells there, which is the expensive and difficult option. And then we've got the shells here, which the answer is virtually identical. Okay, so I'll go back to the Fluent solve to again look at a simple device here, and we'll look at some solution considerations here. Now, it's pretty much the same as solving for a cold flow. There are some additional considerations to take in mind. Number one, residuals. You will find in many cases that you have to tighten up your energy residual. The default to the -6, oftentimes it's fine, but you have to be very, very careful with that. Energy just does take a lot longer to converge. Now, one of the reasons for that, if I go into the run calculation panel, you can see that I've got a pseudo time step for the fluid and a pseudo time step for the solids. Now, this is a steady state solver, but it uses a kind of a false time step to arrive at the steady solution. In many cases, the solid time step for the thermal solution is much, much bigger than the fluid time step. So that's why you can specify different time steps. If I had those the same, it would just never converge. So typically you put in a much, much bigger time step for solids when you're conducting a steady state solution. Okay, so we can run that calculation, and this one does take a few minutes. So I've actually got the data preloaded, and if I load up the residuals, you can see that I brought energy right down to a much tighter tolerance. The momentum converged way before, but it wasn't sufficient. Now, the way that we can check this convergence, if we go to results, you'll probably be familiar with checking mass flow rates through inlets and outlets. Okay, so we compute the mass flow rate and we check that the error or difference is less than 1%. You just do the same for heat transfer. In this case, I'm selecting all the boundaries apart from these interiors here, which I don't need, and I'm computing. And again, I have to make sure that the error there is less than 1%. So everything that's coming in has to leave, and that difference should be less than 1%. And you will find that if your mass flow rate is fine, your energy might not be. So it's very important that you look into it. Okay, so we can look at a few graphics now. And well, let's just look at the temperature through. And this looks kind of nice and reasonable, what we'd expect. Maybe a velocity magnitude. And we'll look at the board temperature. And you see we've got planar conduction through here, which is very important. Remember that we mesh this as a solid, but we could also use shell zones to maintain this planar conduction. So the results, temperature, velocities are straightforward, but generally when we're doing conjugate heat transfer, we're interested in surface heat transfer coefficients, and that's what I want to spend a little bit of time on talking next. Just to kind of confuse things a little bit, if you've not done this before, there's more than one way of displaying a heat transfer coefficient in Ansys CFD. There's actually 5 ways of doing it, and they all have their pros and cons, and it just depends upon what you're comparing it to, what data that you have. So I'm going to pull back the slides here and talk about the options we have available to us. More than one way. We've got what we call a surface heat transfer coefficient, a wall adjacent cell heat transfer coefficient, a wall function coefficient, and a Y+ coefficient. So there's 4 ways of displaying that. And I'll very quickly just go through why we have those and what the differences are. So if we want a heat transfer coefficient that's called wall adjacent, what it does is it calculates the wall face temperature and the temperature on the cell adjacent to the wall. Okay, now that's fine, but then it becomes very sensitive to mesh resolution. So it's not always the best way of plotting this. We then have the surface heat transfer coefficient, and again, it uses a different temperature delta. This is the difference between the wall temperature and a reference temperature that we input. Now that's fine for simple cases, but when we get to complicated cases, it's very difficult to find a meaningful reference temperature. So again, it's there's another challenge there. We then have the wall function heat transfer coefficient, and this extracts variables from the wall functions used in conjunction with 2-equation turbulence models. So it's very dependent upon the way turbulence is handled. And again, it's still mesh dependent. And then we have the Y plus based heat transfer coefficient. And this has been put in recently. And if you're familiar with your boundary layer modeling, you'll know that the Y plus is a dimensionless value that characterizes the boundary layer. That becomes very useful because it makes much more sense to take your reference temperature at a specified Y plus value rather than, say, a fixed distance from the wall or, say, a fixed reference temperature. Okay, so that's why we have different ways of calculating heat transfer coefficients inside Ansys Fluent. Initially, it can be a little bit confusing, but when you actually dig into the equations and they're quite straightforward, and then you understand what your heat transfer coefficient means, it does make sense why we have these different ways of doing it. Okay, so lastly, what I want to do very quickly is to move away from the models and just go through very quickly a real world case. So I'll just spend about 5 minutes on this. And this is actually an exhaust gas recirculation cooler, so it's more of a real case, something that you might find yourself doing. And again, it goes from CHT analysis in CFD right the way through to stress analysis, and then it goes further and starts looking at fatigue. So it's a real end-to-end process, starting from CHT and giving some really powerful insights to a real-world application. So in this case, this is an engine component which reduces emissions by reducing in-cylinder temperatures. Now, these devices are subject to thermal mechanical fatigue, as is common with a lot of devices where you're conducting CHT. So what we've got to do is run a CFD analysis to get a heat transfer coefficient and then pass that on to mechanical. Now, subsequently, that would get passed on to the fatigue analysis. So just a quick overview of what's happening here. We've got the internal mesh. It's basically a heat exchanger. So you've got cooling tubes in here, heat going in the inlet, circulating around the tubes, and then you've got your coolant removing. Now, this kind of device, then, it does have thermal shocks, and that's generally what we're worried about, and that's why you would use this kind of workflow. So we start from CAD. We move over to the CFD CHT analysis. That then is used to provide a heat transfer coefficient across the surfaces to the thermal analysis in mechanical. So in this case, actually, we're calculating the volumetric temperatures in mechanical. And we're actually applying a transient cycle to it, which gives us our stress analysis, time-dependent stress analysis, and then we go into another application which gives us our fatigue analysis. So it's a very complete process, and it shows you what can be done with starting from CHT. So this is the CFD results. We've got a temperature field for 2 operating conditions here. So a low thermal load, the cold cycle, and then the high thermal load, the hot cycle. And we use that to determine our heat transfer coefficients for replicating the thermal shock in Ansys Mechanical. So in the mechanical analysis, we've brought in a CFD CHT steady state cold flow analysis. Then we can apply convection conditions on the mechanical model, and then we can run a cyclic analysis or a thermal analysis mimicking how that component would behave as it's being used. You can imagine it's subject to highs and lows all of the time. So CFD gives us that coefficient, mechanical takes it forward and does a transient stress analysis on it. So if we look at the results for the stress analysis here, we've got our it's got our supportings here. We talked about that in the earlier example, and we've got our equivalent stresses here. So we can see how this structure is responding to a transient thermal shock or stress cycle. And the net result at the end of it is where we want to be. We can then pass that on to a fatigue analysis using another simulation. Okay, so what the fatigue analysis does is it essentially tells us how this component is going to last where it's going to fail and how, and we can use that whole process as a design loop to go back and make sure this kind of thing doesn't happen. So starting from a very, very simple CHT analysis in CFD, you can go a long way, and you can do some fairly incredible things and get some great insights with multi-physics tools that use those CHT results to give you these kind of insights. Now, I realize that I think many of you might be CFD exclusively, but it's hopefully I've demonstrated that it's actually quite simple for you to go above and beyond that. You know, once you've got your CHT analysis done, it's really just the start of the kind of insights that you can get for these sort of applications. So, having talked for 5 minutes more than I planned to, that doesn't happen too often. Just a quick summary then. So, CHT obviously found in a wide range of thermal engineering problems. We can use Ansys Fluent, Ansys CFD to predict the coupled problem, the flow field and the solid conduction. We have to consider the methods of dealing with wall heat transfer, and as you've seen in Ansys Fluent, there's a number of ways of doing that, number of ways of dealing with those difficult thin surfaces and so on using shell conduction. And we've shown some additional capabilities in terms of the data transfers, one-way and two-way thermal FSI with Ansys Mechanical. Okay, so that's concluded what I wanted to demonstrate in the webinar and talk about. Just to say thank you for attending. I hope this has kind of sparked some interest. It's a huge subject, so really the intention was just to say, okay, this is the kind of thing that we can do, and it's the kind of thing that you can do. So I hope that you can follow up on that. If you're existing users, please do have a go at these kind of applications, and I hope this has been very useful. Please, by all means, follow up, reach out to us. We'll be happy to answer any questions, and also keep an eye out for future EDRMedeso webinars. We do like to deliver these, and we know that they're helpful for everybody, so keep your eyes peeled for future webinars, and look forward to talking with you again. Thanks very much, and have a great afternoon.